Welcome to the channel. I'm Carlos Ortega, and I'm excited to explore the amazing worlds of physics and chemistry with you.
We view the steel and concrete infrastructure of our cities as permanent, rigid, and unchanging. Thousands of tons of metal and stone seem like the most stable objects in daily life, but that stability is deceptive. During an intense heat wave, solid steel railway tracks can absorb enough energy to buckle and contort, turning a straight line into a dangerous curve. Even the most famous monuments are in constant motion. Depending on the season, the Eiffel Tower's iron frame can grow up to 6 inches taller in summer than in the midwinter cold. This movement is caused by thermal expansion, a physical process that forces materials to change their physical dimensions as their temperature shifts. To keep a city standing, engineers have to account for these invisible movements, designing structures that can shift and breathe along with the temperature of the air around them. Understanding why a bridge expands in the sun requires us to look past the steel beams and focus on what heat actually represents at the atomic level. On this scale, heat is simply kinetic energy, the physical vibration of molecules. Even in a solid, particles are constantly jiggling. As temperature rises, vibrations become more violent. The particles strike one another with more force, demanding more space and pushing the group outward. This is a consistent physical pattern. As most matter gains thermal energy, it physically expands. As it loses that energy, it contracts. The collective pressure of billions of these microscopic collisions is what provides the mechanical force necessary to bend a solid railway rail. You can see this force in a simple laboratory proof. A solid metal sphere is manufactured to be just slightly too wide to pass through a matching metal ring at room temperature. But when that ring is heated with a blowtorch, its molecules vibrate and spread. The opening grows just enough for the sphere to drop through. Modern engineering relies on calculating these exact microscopic changes to prevent large-scale structural failure. This is a thermal expansion joint. By looking at these interlocking metal teeth, you can see the literal gap left for the material to expand into during the hottest part of the day. Without these gaps, the internal pressure generated by expanding materials would eventually cause the concrete to crack and crumble. Up to this point, the rule seems predictable. Heat expands and cold contracts. But water behaves differently. If you leave a glass bottle of water in the freezer, it doesn't shrink into a smaller block of ice. It expands with enough force to shatter the glass. As water freezes, its molecules slow down and lock into a rigid hexagonal lattice. This specific geometric structure actually requires more space than the chaotic arrangement of liquid water, forcing the volume to increase as it cools. This microscopic deviation is why icebergs float. Because water expands as it freezes, the solid state is actually less dense than the liquid state. This exception prevents lakes and oceans from freezing solid from the bottom up, creating the specific conditions that allow aquatic life to survive the winter. To see the next layer of this behavior, imagine standing on a beach on a clear summer day. The dry sand and the ocean water are both being hit by the same sun, absorbing the exact same amount of solar energy. Yet the sand becomes painfully hot to the touch, while the water remains cool. The difference lies in how different materials respond to the energy they receive. While we know heat causes movement, we still have to explain why some substances spike in temperature almost instantly, while others barely change at all.